Today we are starting a new chapter, Chapter 4, Force System Resultants. In this lecture, we are going to discuss what is a moment and how we can define moments in 2D and 3D dimensions. When a force is applied to a body, it will produce a tendency for that body to rotate about a point, let's say O here, that is not on the line of action of the force F. This tendency to rotate is called as moment of a force, or simply the moment, and it is denoted by capital M. Sometimes the moment can be also called as torque. So torque and moment can be used interchangeably. Moment of a force is a vector quantity. Therefore, it must have a magnitude and direction. For example, in this example, we are applying a force to the wrench here. We are applying a force, and this force will generate a moment at point O. As you can see, the line of action of F here, the yellow color shows the line of action of F, is not intersecting with point O. So this force can generate a moment, a rotation at point O. As you can see, the force Fx and the distance between point O and force here is in xy plane. Therefore, the generated moment will be perpendicular to xy plane. So it will be in z axis. We can calculate the magnitude of the moment. If we know the magnitude of our force, here F, and the perpendicular distance between point O and force F, let's say D. So magnitude of the moment will be calculated by multiplying force with perpendicular distance. The perpendicular distance between point O and the line of action of F is called as moment arm. As the magnitude of moment is calculated as force times distance, the units of moment will be Newton meter or pound feet. Okay, in this example, we are applying a force to the wrench, and the magnitude, we know it is magnitude, and if we know the perpendicular distance between point O and F, let's say here dy, then we can calculate moment generated at point O. Here there are some good examples to understand the concept of moment. Wrench and bolt system. If we apply a force to the handle of wrench, here we are applying F to the wrench, it will tend to turn the bolt about point O. And it will rotate it in Z direction. The magnitude of moment will be F times D, moment arm. The perpendicular distance between point O and line of action of force F. So we can say that the magnitude of the moment is directly proportional to the magnitude of F and the perpendicular distance or the moment arm D, F and D. This means that the larger the force or the longer the moment arm, the greater the moment or the turning effect. For example, in this case, we are applying the same magnitude of F, but it is not perpendicular. It is applied at an angle that is smaller than 90 degrees. So it will be more difficult to turn the bolt since the moment arm here, the vertical distance will be d prime. D prime will be smaller than, in that case, d. So to generate the same moment, we have to apply more force. Okay, let's consider this one. If we apply the force along the range, here we are applying force along the range. This means that point O and line of action of F will intersect. This means that the moment arm will be equal to 0. So the moment of F about point O will be equal to 0. This means that this force will not produce a rotational effect. Remember that we thought that moment is a vector, so it has a magnitude and direction. We saw how to calculate its magnitude, and now we are going to learn how to decide its direction. The direction of moment is defined by its moment axis, which is perpendicular to plane that contains the force F and its moment arm D. Here, in this example, we have a force F and we know the perpendicular distance, moment arm of F, here D. F and D here is in XY plane. So the generated moment will be perpendicular to XY plane. So it must be in Z axis. While deciding the direction of moment, we are going to use right-hand rule. Fingers of the right hand are curled such that they follow the sense of rotation. Here, the applied force F will rotate in counterclockwise direction. And the thumb will point the moment axis. So it gives the direction and sense of the moment. So here the thumb is in z direction. Generally, counterclockwise direction is taken as positive and clockwise direction is taken as negative. In that example, our fingers are curled as counterclockwise direction. So the generated moment will be in z direction and it will be positive. It will be in counterclockwise direction. If more than one force lies in an xy plane, then the moment produced by each force about point O will be directed along the positive or negative z-axis. So the resultant moment, here denoted by mr, at point O will be equal to the sum of moments of all forces. While writing this, be careful with the direction of the moments. For example, m1, the moment of force F1 produced at point O, will be equal to the F1 times D1, and it will rotate the body counterclockwise direction. So it means it is in positive z-axis. But for F2, it will rotate the body in clockwise direction. So its moment will be in minus z direction. So we are writing minus F2 times D2. And for F3, it will rotate the body in counterclockwise direction. So it is in positive z-axis. So it must be plus F3 times D3. Be careful with the tendency of rotations. Cross product or vector product, they are the same, is a useful approach to find the vector which is perpendicular to a plane formed of two vectors. Here, the vector A and B. The cross product of A and B yields vector C, which is perpendicular to A and B. We can calculate the magnitude of the resulting vector C as the magnitude of A times B and sine theta. Here, theta will be the angle between the tails of A and B. This is the theta. To decide the direction of the resultant vector C, we can apply right hand rule again. So our fingers will be curled from A to B, as in this one, A to B. So it means that it is in counterclockwise direction. So cross product of A and B will generate vector C in Z, positive Z direction. As we know the magnitude of C here, we know the magnitude of C. We can calculate the resultant vector C. If we multiply its magnitude with the unit vector of C. This unit vector will define the direction of C. Okay. These equations are very important. You should understand them. They are very important. You should also know the laws of operation for cross product. Cross product is not a commutative. It means A cross B is not equal to B cross A. Okay, here A cross B will generate vector C in positive Z axis. However, B cross A. Okay, B cross A. It is in clockwise direction. So the resulting vector C will be in minus Z direction. So we can say that A cross B will be equal to minus B cross A. Scalar multiplication and cross product will obey the distributive law, but it is not associative. While finding cross product of Cartesian vectors, be careful with the unit direction vectors. Okay, again, this is our right coordinate system, right hand coordinate system. In x direction I, in y direction j, and in z direction k. Okay. I cross j means that the magnitude of I, which is 1, the magnitude of j, which is 1, and the angle between I and j. These are perpendicular, so the angle will be 90. So sine 90 is equal to 1. And the unit vector, the unit direction vector will be in z direction. So it will be k. So it means that I cross j is equal to I cross j is equal to k. Here I cross j equal to k. Let's see now j cross I. So j cross I, it will be in clockwise direction. So it will generate minus k. Where is it? J cross I. It will be minus k. Okay, for example, J cross K. J cross K. Counterclockwise direction. So it will generate I. J cross K. It will produce I. Let's say I cross K. It will be in clockwise direction. So it will generate minus J. I cross K will be equal to minus J. Okay. What about I cross I? As the angle between I and I will be equal to 0, sine 0 will be equal to 0. So I cross I will be equal to 0, J cross J will be equal to 0, and K cross K will be equal to 0. Okay, just remember right-hand coordinate system and you can decide the directions of each term. Okay, let's say we have vector A and vector B and they are given in Cartesian vector notations and we want to calculate their cross product. So apply distributive law and this cross product will be simplified to this one. Okay, we can apply cross product to calculate the cross product of two vectors in Cartesian vector notation by applying distributive law. But it is a little bit complex. So to calculate the cross product of A and B, we can apply determinant. It is more easy. So what we will gonna do to calculate the I component. Okay, let's cancel these terms and we are going to multiply AY times BZ, A times EY times BZ minus AZ times BY. This is the components of I. To calculate the components of J, okay, we are going to cancel J component and we are going to multiply AX with BZ and minus AZ times BX. Here. This is the J component of While calculating J component, do not forget the minus sign before the J. Okay? You should add a minus sign before J. And to calculate K component, okay, we are going to multiply AX with BY minus EY times bx. Here, this is the k components of k. Okay, please work chapter 4.1 and chapter 4.2 from the book.